Hi, everybody. Welcome to this talk on heterogeneous programming in C++ with Sickle 2020. My name is Michael Wong. Along with my colleague, Gordon Brown, we would like to demonstrate to you how you can use, especially the latest upcoming Sickle 2020, to program heterogeneous devices, accelerators in modern C++. So just a couple of a quick slide about what our company does. CoPlay does a lot of things that has to do with accelerated GPU computing. So introducing my colleague, Gordon Brown. He is a principal engineer. He has a background in C++ programming models for heterogeneous systems. He's been a principal engineer with CoPlay, and he's worked on the Sickle implementation called Compute CPP since its inception. He's been a massive contributor to the Khronos Sickle standard and to C++ executive and heterogeneous programming for 2 years in SG1. A little bit about myself. I'm a distinguished engineer with CoPlay. I'm also the chair of Sickle, the heterogeneous programming language, as well as being the chair of the C++ directions group. I've had to wear many hats over the years. Recently, I'm now the chair of the C++ SG19 on machine learning, as well as SG14 on games development, low latency, financial trading, and embedded. My career has spanned from being a compiler, developer, engineer, writing exception handling code and how to actually implement exception handling C++ and object models, to high performance computing as well, and then now towards embedded computing with autonomous vehicles. So I've been doing a lot of research lately in terms of the safety of autonomous vehicles, machine learning, and AI models. But I also still stay with my first love of being involved with programming models and heterogeneous programming models specifically. So some acknowledgement. A talk like this wouldn't have been possible without numerous internal and external contributions, and I want to make sure that we credit them wherever credit is due. I even stole this disclaimer from them, so there might still be errors that remain, and any that remain are all their fault. No, actually, it's our fault. We will also use logos from various companies, and we just want to make sure that those are credited as we go. So much of this talk is going to break down into three. As in almost all my talks, I like to just separate into three items. We're going to talk about Sickle past, where we're going to talk about the origin of Sickle, some of the lessons learned, and the impact of Sickle on the ecosystem. We're going to talk about the Sickle present, where we are right now, that Sickle being used as a general purpose, high-performance programming model. And we're going to show you a deep dive of what's coming in Sickle 2020. Now, Sickle 2020 has not been finalized yet, but we are allowed to show you many of the features that are already essentially enshrined in the standard. Then we're going to look at the Sickle future with the ecosystems that's rapidly gaining momentum, and that Sickle now acting as an independent working group and further super tight alignment with ISO C++, contributing in both directions, taking stuff from ISO C++ and contributing our knowledge of heterogeneous programming, along with many other people into ISO C++. So a little bit about what Sickle is. Khronos is a related consortium of standards, and they have many of them. I would just point out that Sickle is a part of the Khronos portfolio of open specifications and belongs in the parallel computation group, along with things like Spear, OpenCL, and NEF, OpenVX. But as such, we're also involved with things like vision, inferencing, and machine learning. It is a single source C++ parallel programming language framework that takes standard ISO C++ application code, even TensorFlow, and then compiles them with a host CPU compiler and a device Sickle compiler, which generates code for many kinds of devices. The reason I want to point out that this is single source is because there has been many attempts at this, and some are not single source. They require separate source. Some isn't capable of marrying with modern C++ all the way up to templates or even up to C++ 1720. Sickle, because of its tight alignment, keeps up with all of those things. all the steps of ratifications to C++, as well as staying with single source, which we believe has now more or less definitively been proven as the best programming model for heterogeneous computing. So the story so far, so in 2018 at IWACO in Oxford, I showed this slide setting the stage for Sickle Pass, when we had Sickle 1.2 in 2015 and Sickle 1.2.1 in 2017, and their alignment with C++11. The following year, Compute CPP became the first conformant implementations. The early implementations, there were Compute CPP and Tricycle, which allowed people to try it out. And after a couple of years of feedback, that's when we came out with Sickle 1.2.1. The following year, Compute CPP became the first passing the conformance test. And over the next 2 years came HipSickle and then Intel's DPC++. And there were various extensions that's been proposed since then. We've open sourced the Sickle 1.2.1 conformance in May 2019, and DPC++ recently has been extended to support Cuda. We're going to talk a lot more about that in the rest of this talk. Okay, starting on the second step, which is Sickle Present. So today, I'm really happy to unveil this slide about the possible future roadmap of Sickle, where in 2020, we plan to release first a provisional provincial, which already has been done for public review and feedback, leading to a final potentially in Q4. We plan this version to be based on C++17 on the right, you can see. This means it enables exciting C++ features like CTAD, class template argument deduction, and deduction guides that makes the code less verbose. There are also a number of other great features, which I will highlight. You're going to see that we released Sickle 1.2.1 in 2017 and previously 1.2 in 2015. And if you were to predict that we seem to be settling down to a cadence of releasing new releases every 1.5 to 3 years, matching to the ISO C++ schedule, you will be correct. This is because we have adopted basically the same bus train model of delivery. You will also see that we have changed the naming scheme from what it used to be aligned with OpenCL versioning to naming by year, just like ISO C++. And this allows us to be now based on multiple backends in addition to OpenCL, which still remains our primary backend. But now you can have different backends like OpenMP, Cuda, Vulkan, Cocos, Raja. You will also see that we're projecting in tentatively that a future Sickle is going to be released after 2021. Expect the exact version, obviously, to be named later, and will likely be based on C++20, which will be released at the end of this year. Now it's been pretty much confirmed. So this shows essentially our tightest ISO C++ alignment, injecting our heterogeneous knowledge into ISO and adapting C++ features. Next slide. So I want to show what a pleasure it has been to see Sickle growth since 2016. By my count, starting from when I first attended in Frankfurt at the face-to-face meeting to the last face-to-face meeting in Barcelona before it got all shut down, we doubled in size by 2 times, from averaging 15 people to over 30 people in the last meeting. We continue to have strong attendance from Intel, Xilinx, Codeplay, AMD, ARM, Qualcomm, A&L, Argonne National Lab, University of Salerno, University of Bristol. Externally, we've been active in CppCon, giving Sickle talks and tutorials in 2016, 17, 18, and 19. Thank you to the CppCon Programming Committee for allowing us to do that. We have also had BOFs in supercomputing 17, 18, 19. In the last year, we actually had 2 separate BOFs, one that is a standalone Sickle BOF, and another, along with another one on showing how heterogeneous ISO C++ can benefit high-performance computing. At Supercomputing 19, the number of Sickle events exploded from 2 to 3 Sickle events in 2018 to 6 to 8 Sickle events that's related in the forms of papers, talks, BOFs, keynotes, and various workshops. So as you know, in the past, Sickle held an annual workshop called DHPC++. I know it's a mouthful. Never said that we were great at acronym naming. Remember RAII? So that was a workshop in IWACO, as it was not yet its own working group yet. So on September 22nd, 2019, I'm going to declare that as Independence Day for Sickle, because that's when it became its own working group within Khronos, and now it's held as an integrated conference with IWACO called SYCLCon. I really wish it was called Cyclone, but hey, what the hell, I can't get everything. Okay, so I show here how the commits have spiked, have grown in our normal GitLab. You can see from the spikes when we're about to release and the massive recent spikes in activity as we prepare for releasing Sickle 2020. Thank you, Renan, for building up these slides for us. So now we want to switch to looking at what might be in Sickle 2020, which you can see is still under construction. So a lot of these contents is caveat emptor, they could still change, okay? Now, the question here is how do you get involved, even if you're not a Khronos member? As you can see, we are now got permission with Khronos to move toward a much more open model with Sickle, because it's not really a language that is tied to any hardware. So there's no real secret hardware things that we have to keep that secret. It's really a software specification, just like C++ is. So now we can take public contributions or fixes or even features, as well as suggestions for new features. You can even now see many companies' features on their Sickle feature Git repo. These are the ones that have been agreed by the Sickle working group to be made public early, so you can contribute into it. You can be an advisory group member, so that you don't have to be part of Sickle. You don't have to pay, and you can advise. You can get early looks at our specification. So this enables essentially a more rapid feedback cycle. So the way it works is really simple. The GitHub hosts the latest public ratification. That's the public GitHub. And it allows open access and contributions of merge requests to fix existing features on the GitHub. The Khronos GitLab is the private one, and it hosts the next version of Sickle that's available to the working group. Some Sickle features are deemed open by the working group and is hosted on company Git repo. You're going to see the links for Coplay, Intel, Xilinx, Hipsico later on at the bottom of the end of the slide talks. Other Sickle features are developed under Khronos IP within the private GitLab, and both groups progress from extension to core. And after ratification, they move the GitLab ratify spec to the GitHub, the public one, and then we do conformance tests and tests for conformant implementations, and then we just keep iterating. So this is the main slide. If you forget anything, try to think about this one slide where it shows that what might be in Sickle 2020. And in the top right box, our general logic philosophy that we have followed in our change from Sickle 121 and Sickle 2020. We want easy integration with C++ 17, less verbose language that has smaller code and simplify common patterns. We want to enable multiple backends, but simplify interoperability, while at the same time easing porting of C++ application to Sickle, improving programmability. We want to strike a balance for performance and stability by enabling backwards compatibility with previous release, but also selectively breaking API to achieve higher performance. We expect that breakage to be minor from Sickle 121 to 2020. On the top left, you will see some of the features we already have, which we're going to have talks about in the rest of this talk. I draw your attention to what's called generalization, program modules, host task interoperations, interoperability, unified shared memory, and in-order queues, and call out our Nvidia support. And a lot of this Gordon is going to go into detail about. In the bottom right, you're going to see there are many features in the pipeline that, and on the far right, you're going to see that our main goal is converging Sickle and ISO while continuing to strongly support OpenCL and driving to support even more kinds of chips, including other kinds of accelerators, machine learning, and AI processors. The main diagram illustrates our philosophy moving from Sickle 121 to Sickle 2020 and iterating this cycle with new releases every 1.5 to 3 years from the previous to the next release. So at this point, I want to hand over to my colleague, Gordon Brown, who's going to go into amazing details about some of the Sickle 2020 that you can benefit from. Thank you.
Okay, thanks very much, Michael. Hi, everyone. Thank you very much for watching this talk. So now in this part, I'm going to take over and go into a bit more of a deep dive into some of the features that are planned for Sickle 2020. So here I have a kind of overview of some of the major features, like what Michael just mentioned, the generalization, unified shared memory, There's other things like subgroups, group algorithms, a lot of simplifications. There's a feature called modules. That's not to be confused with C++ 20 modules. It's a different feature, a slightly confusing name. One thing to note, though, that this is as Michael said, this is a provisional specification, so it's still subject to change. Although the reason that we release a provisional spec is that the working group are pretty confident of the features that we're proposing, and we're looking for kind of feedback from implementations and from users. So it's a very strong indication of what SYCL 2020 will look like, but it is still subject to change. Unfortunately, I don't have time to cover all of the features I'd like to, but I'm going to focus on these 5. So backend generalization, unified shared memory, in-order queues, host tasks, and some API simplifications. So starting off with the backend generalization. So Michael went into this a little bit earlier. When Sickle was first released, Sickle 1.2 and then Sickle 1.2.1, it was entirely based on OpenCL 1.2. And this is because it was originally designed as a high-level programming model for OpenCL specifically. So it can only officially target OpenCL devices. There are implementations or work-in-progress implementations that do support other backends, and we'll see some of those later. But officially as a kind of ratified conformant implementations, you can only support OpenCL devices. So one of the things we wanted to do once we saw that there was opportunity for Sickle to support other programming models as well. We wanted to move Sickle in 2020. We wanted to move it to a more generalized heterogeneous programming model. So what this means is Sickle 2020 can support devices from any backend, including OpenCL. The execution model and memory model remain the same, obviously with improvements from 2020. And the API is largely unaffected, not including additional features introduced in 2020. And so what is a backend in the context of Sickle now? So a backend is essentially any C++ programming model, a C++ based programming model. So this could be sort of separate compilation models like OpenCL or Cuda. Could be like Pragma-based programming model like OpenMP, or could be even something like Vulkan, or a library solution like TBB. Or essentially, a backend can be implemented on top of any C++ based programming model. So this slide may be familiar to people who've seen Sickle talks before. This is the kind of high-level Sickle ecosystem. So you have Sickle applications, and they're written against this Sickle API, so it's a template library. And then underneath that, you have a Sickle runtime, which can target different devices. And in the past, you would have a host device and then other OpenCL devices. However, in Sickle 2020, you can now have other backends. So you still have the host backend, but now there's potential for other backends, such as Vulkan or Cuda or anything like that. Now this diagram here is just indicative. It's not representative of any specific implementations. It's just to kind of give you an idea of the possibilities. A couple of things to focus on. Every Sickle implementation, just as with 1.2.1, must have a host device and must have a host backend in this case. So the host device is essentially an emulated Sickle device that follows the same execution memory model guarantees as any other device, but it runs on the host CPU and can be useful for debugging. Next, we have every Sickle implementation must also have at least one non-host backend. So it could be OpenCL, or it could be Cuda, or it could be any other backend. To see how that looks like in the kind of topology of devices that are available when you run a Sickle application. Originally in Sickle 1.2.1, you would have platforms and devices. Devices are the physical devices that you're targeting, and platforms are essentially the vendors. But now we have this additional layer for the backend, and you can have different platforms and devices from different backends. one thing to note here is the host device is associated with the host platform as it was in 1.1, but it's now associated with the host backend in 2020. Another important thing to note is that because Sickle 2020 can target multiple backends, these different backends are generally completely independent APIs. So, for example, here we have OpenCL and Cuda. So there's one thing to be aware of is that the same physical device could be represented by multiple backends. So the same physical GPU could be reported by OpenCL and by Cuda. So often you may want to just target one backend, but if you were to target multiple backends, you have to be careful of this to avoid contention over the resources. So with this in mind, taking a look at the kind of different ways that you can write Sickle code. So we kind of define this as three different categories. You know, there's generic Sickle, interoperable Sickle, and then vendor-specific Sickle. So first of all, generic Sickle is essentially an application written against the core Sickle specification. And any application written against core Sickle spec is portable across any implementation. So it's a standard API. It doesn't matter which backend the implementation supports, the same code will run everywhere. Obviously, that doesn't give you entirely performance portability. It's sort of API portability. There's still, often you will still have to tweak applications for different devices or different backends to kind of achieve optimal performance. Next, we have interoperable Sickle. So just as in 1.1 with OpenCL, Sickle 2020 has an interoperability API, which allows you to hook into the underlying native backend, so that'd be OpenCL or Cuda or whatever the API of your backend is, and do things specific to that API. And this is less portable. So any interoperable Sickle code will only be portable to implementations that support the same backend. And there will be many implementations that support the same backends, but some backends may only be supported by one implementation, perhaps. And then lastly, we have vendor-specific Sickle. So this is the least portable. So in some cases, you may want to use a feature that is specific to one vendor. It could be an extension to support a particular hardware feature. Many implementations of Sickle provide their own extensions to provide functionality that's beyond what's in the core specification. And often these features will find their way into the core specification after they've been kind of reviewed and considered for the spec. But if you use these features, you can do that, but then that limits you to one specific implementation. So to kind of give an overview of what implementations of Sickle are available, there's four main implementations. CodePlay has a commercial implementation called CPP. This is the first conformant 1.2.1 implementation. There's also DPC++, which is an open source project led by Intel. And then there's another open source project called Tricycle, which is led by Xilinx. And then there's a fourth called HipSycle, which is led by Heidelberg University. And all these implementations vary in the backends that they support. Across the different implementations, there is OpenCL, Cuda, OpenMP, ROCm, and even some standard CPU libraries. And between these different implementations, they also support a very wide range of devices. So I believe across this we have Intel, AMD, ARM CPUs, Intel, AMD, ARM Mali, PowerVR, and Nvidia GPUs. And also through CppCP, there's support for the Renesas RCAR platform as well for automotive. So depending on what your platform is, you may want to choose one implementation or another. But one feature that's been requested quite a lot is support for Nvidia GPUs. And so CodePlay did some work over the last year to introduce support for Nvidia GPUs through a Cuda backend in DPC++. So DPC++ is the open source implementation. So it's a standard SYCL 1.1 implementation, but also has a number of extensions for optional features. And many of these features have ended up in the SYCL 2020 spec. But it also has a plugin API for allowing you to add other backends. And this is how we introduced the Cuda backend. So just to give a kind of idea of how to use this, this is an open source repo, and there's regular, stable, and daily releases. So you can download that and check out. And there's a getting started guide, so you can try it out. Just to give an idea, the way you'd use this is essentially you call the Sickle compiler as normal, but you would specify the Nvidia Cuda triple, and then when you run the code, you specify an environment variable to set the plugin API to target the Cuda backend, and that's essentially it. As I mentioned before, because Sickle is a portable API, the implementations are standard. So code written against one Sickle implementation will work on any other implementation. So to run on Nvidia GPUs, all you need to do is essentially change the device selector so that it picks a Nvidia GPU, and then that'll run on the GPU. Just to give a snapshot of the current performance of this, this is performance figures using the Babel Stream benchmark. We're on a GeForce GTX 980, and as you can see, the performance of Sickle running on the Cuda backend through DPC++ is very comparable to native Cuda. Yep. Okay, the next feature I want to cover is some API simplifications. So one of the big things about Sickle 2020 is it now supports C++17, which has allowed us to introduce some new features and simplifications to the API. So this is a typical Hello World application in Sickle 1.2.1. So here we allocate some vectors for input and output data. We create a queue to enqueue some work to, and then we create these buffer objects which will manage the data to and from the device. And then we submit a command group. Inside that, we create accessors to say you want to access that data on the device, and then we call this parallel for to enqueue the kernel. So the lambda inside the parallel for there is the actual function that runs on the device. So to go through some of the simplifications, now that Sickle 2020 is a sort of general programming model, we've changed the header file to now be Sickle rather than CL, and the same goes for the namespace. Another change we made was that it's no longer required to name kernel functions. So in Sickle 1.2.1, you would have to use a type to name the lambda expression you use for your kernel name, and that's no longer necessary. Next, we added some global variables for the device selectors, so you don't have to instantiate the new ones every time. And next, one of the biggest simplifications we made was that we now introduce CTAD and deduction guides, so to remove a lot of the template parameters when creating buffers and accessors and ranges and that sort of thing. One thing to note with that, though, is that when you're with CTAD, it was necessary to introduce some tags for specifying specific parameters. So in this case, it's the access target. So here we have read-only and write-only instead of the access target template parameter. So it does the equivalent thing. Okay, the next feature I want to cover is host tasks. So in Sickle 1.2.1, there was no way to call arbitrary C++ code from a task graph. So when you enqueue a chain of work in Sickle, you'd have multiple functions running connected to each other with dependencies, but there's no way to inject kind of arbitrary C++ code or a callback without synchronizing back to the host. So Sickle 2020 solves this by introducing the host task API. So host task is quite useful for callbacks. You can essentially have a C++ code that's triggered when a kernel finishes. And it can also be used to interoperate with the back-end native programming models, which we'll see in a second. Okay, so this is what the host task looks like. It's very similar to the other APIs like Parallel 4, but the code inside here is native C++. And host tasks are scheduled in a very same way as kernel functions. They follow the same memory model rules, so they have dependencies based on accessors, just as with kernel functions. The code inside the host task is native C++, so this can include calling standard C++ libraries and doing I/O. And the usual kernel function restrictions on things like recursion and dynamic allocation and things like that don't apply in here. When you're using a host task, you use accessors to kind of request access to data and create your dependencies, just as with kernel functions. Here we're creating host accessors by calling get host access, and this makes the data available on the device to be accessed when this task is run. And then these accessors can be used to access the data inside the host task function. The other feature of host tasks is the interoperability. So in order to enable this, you simply pass this optional interop handle parameter to the host task. And then that handle can be used to retrieve the backend API objects associated with any Sickle objects. One other thing to note with this is when you're using a host task for interoperability, you want to request the data to be available on the device because you want to access the data through the backend API memory objects, the OpenCL memory objects or the Cuda memory objects. So here you just do a regular get access to get to access the memory on the device. And then these accessors, because they're pointing to memory on the device, but the host task itself is running on the host, you can't access those accessors directly, but you can use them to retrieve the native backend API objects. Okay, so the next feature, I think one of the most exciting ones is unified shared memory. So unified shared memory essentially provides an alternative pointer-based memory management model, alternative to the buffer accessor model that you've seen in Sickle 1.2.1. Now, Sickle 2020 still has the same buffer accessor model, but this is now an alternative model, which has some benefits. So USM provides a unified virtual address space, which means you have consistent pointers across the host and device. So it means if you allocate a pointer, that you have the same value on the host and device, which means the pointer can be passed back and forward without the need for accessors to marshal them back and forward. This allows you to have pointer-based structures like linked lists or other kind of things. Also, USM has an explicit memory management model, which means that rather than having automatically moving your data and managing dependencies like with buffers and accessors, it's explicit. So all of the dependencies and memory movement has to be done manually. And finally, it also allows, on some devices, it allows shared memory allocations, which are memory allocations which can be seen by both the host and the device. So to give an idea of what this looks like, so USM memory allocations essentially return a pointer that is consistent across the host and device. So you can pass this pointer back and forward between the host and your device, and they'll point to this an address in this virtual address space, which then points to the underlying memory, either in CPU memory or on your GPU memory. And then this is the movement of the data between the different actual physical memory regions is managed by explicit memory operations. So this allows you to do things like create a linked list, because when you allocate memory in USM, rather than allocating like a buffer of elements of a specific type, you're allocating a region of memory, a span of bytes. So then any pointer within that region of memory can freely point to other addresses within that region. So this one of the nice things about this is it makes it a lot easier to port existing code, C++ code to Sickle. So the way that you copy memory back and forward is through the Sickle Mem Copy Operations. And so the Sickle runtime doesn't perform any data dependency analysis. So all dependencies are managed manually. Some platforms, as I mentioned, some platforms will support variants of USM where memory allocations should be shared between the host and devices. In this case, no explicit memory operations are required. You just copy the pointer across and it can access the data automatically. So here's a kind of brief summary of the different versions of USM you can have. There's more detail of this in the Sickle 2020 provisional specification. But the features that I've covered so far, consistent pointers, pointer-based structures, and explicit memory, explicit data movement, these are supported by all forms of USM, and including the minimum, which is explicit USM. And then from there, there's kind of increasing versions of USM. Restricted USM supports the shared access, so that's having a single memory allocation accessible by both host and device. Concurrent USM takes that, but also allows the host and device to access at the same time. And then system USM essentially allows standard allocations with like malloc and new. So that means you don't need to use the Sickle memory allocation routines to allocate memory. And different devices will support different levels of USM. The minimum is explicit, but everything after that is optional. So now I'm going to run through the example that we had earlier, but rewriting this with USM just to show how this looks. First of all, we just calculate the size of the data in bytes for the vectors, because this will be useful later. So first thing we do is we allocate the memory on the device. So we do this by calling malloc device. So here we allocate number of elements of float, and we specify the queue to say which device we want to allocate on. And then the pointer returned will be consistent across the host and device, but only dereferenceable on the device. So malloc device is specifically allocating on the device. Next, we perform Mem Copy Operations, which will copy the data from our vectors to the device allocations. And these return events which can be used to synchronize the completion of the copy operations. Next, we call parallel for. One thing you'll notice here is that we don't create a command group, and this is because with USM, because we're not using accessors, you can skip the command group and call these shortcut functions, which is called parallel for directly. And then this operation also returns an event that can be used to synchronize the completion of the function. And inside the kernel itself, we retrieve the ID. The reason for this is that with accessors, they can be subscript or indexed using the ID directly, but here we retrieve the actual linear ID as an integer, so we can index the pointers. But we perform the same vector addition as before. Finally, we do another mem copy to copy the result back, similar to before. And again, we take the event. And at each point, each one of these commands, we're also passing in the events from the previous commands to chain the operations together. So this creates a kind of dependency queue of all the different operations that are being performed. And then at the end, we wait on the final event to wait for all of the work to complete. And obviously, once we're finished, we have to free up the memory. One thing to note, this is the Sickle API free, not the standard C++ free. You'd only be able to use the standard malloc free with system USM. There's also a USM allocator that I'm not showing here, which performs allocation and deallocation in this way, which is useful if you want to do it that way. Okay, finally, in-order queues, which is kind of a small extension to this. So in order versus out of order. In order execution means that all commands are executed in the order that they're enqueued, so in a strict ordering. Out of order execution means that commands can be reordered as long as they satisfy the memory model. And this is generally how Sickle queues have worked in Sickle 1.2.1. So Sickle queues are by default out of order. But now in 2020, a queue can be created as in order by using this in order property. So we're going to take the example we just looked at and do that. So what we do is we specify this property to the queue constructor called inOrder. And essentially this tells the queue that everything that's in queue to it should be executed in the order that it was submitted. So there's no reordering allowed. What this means is that since the queue is in order, there's a guarantee that there is going to follow a very specific order. We don't need to chain these different commands together with events anymore. So this simplifies the usage. And this is quite useful if you know that you don't want to reorder. You know that you're going to execute work in a particular order. Then order queues can be very useful and can simplify the API quite a lot. Okay, and that covers all of the Sickle 2020 features that I have. And now I'm going to pass over to Michael again to go into Sickle future. Thank you.
Okay, thank you, Gordon. That was great. I love looking at how those features, how we're getting more and more C++17 alignments here. So I'm going to talk a little bit about Sickle future and where we're planning to go as a group. The first thing that I want to look at is what is the Sickle ecosystem, and it's rapidly growing. So this slide in particularly highlights the already large and growing Sickle ecosystem, starting with the implementations on the left that Gordon is talking about, HipSickle, One API, DPC++ from Intel, our Compute CPP, HipSickle. And then there are many research papers that are growing. And of this, I want to point out the Exascale computing project and the Celerity for Sickle cluster. The Celerity programming environment seeks to essentially enable developers to scale C++ applications to accelerate the clusters with pretty much relative ease, essentially leveraging and extending the Sickle domain specific embedded language by having users provide minimal information about how data is accessed within the compute kernel. Celerity essentially automatically distributes the work and data. So think about MPI, but running on accelerated C++ with Sickle. ECP, the Exascale computing project, allows Sickle to run on exascale supercomputer systems using Intel chips being built right now at Argonne National Lab. And it's aiming to reach exaflop computing, that's 10 to the 18 floating point operations per second. With that, you can now essentially start mapping the universe, much bigger genome, climate change, disease, proliferations and spreads. So much of this is going to be, has been shown in a keynote by Hal Finkel at IWACO this year. And there are now also several benchmarks involving Sickle. And I want to call out University of Bristol's Babel Stream that measures the performance portability of Sickle, taking along with many other acceleration languages like OpenMP, OpenCL, Cuda, and OpenACC. Over time, this has increased to a suite of 4 to 5 benchmarks, including TLEAF that measures acceleration performance. There's also Intel's Jeff Hammond's programming research kernel, or PRK. It's a suite that contains a number of kernel operations plus a simple build system intended for a Linux compatible environment. Most of the code relies on open standard programming models using Sickle, and testing the productivity of using these models and executing on many computing systems. His one interesting conclusion was that most of these program models, while it certainly was helpful in terms of increasing the productivity, there was an older one that was Boost.compute that he was looking at, and he found that converting them to templates made it not as easy to use. So take a look at his work. There's also many libraries now in Sickle supporting linear algebra, machine learning, and parallel acceleration. And at the bottom, you're going to see all the active working group companies that are attending the weekly calls, as well as all the face-to-face that are going on. So in this slide, I want to point out what an extraordinary adoption it has been to see Sickle grow into the high-performance computing space with the Aurora supercomputer in exascale computing. I attribute this to the fact that we lead ISO C++ with a language that uses standard C++, but augmented with heterogeneous dispatch, but not for any one device, but for a democracy of many different device kinds from many different vendors. which is the promised road to getting to exascale computing using accelerator. You see, these guys, their code lasts for 10, 20 years, but their hardware is always almost brand new, but it only lives for another some 5 years. Every 5 years or so, they switch vendors and uses a different hardware. So you see here that Sickle, through Intel's DPC++, is adopted to be the programming model for Aurora, the first Coral exascale computer using Intel processors. Now, there are actually 2 more coming. They're called Frontier and El Capitan, and they're going to be delivered with AMD processors, both CPU and GPU. I will point out that Sickle can run on ROCm, as one of our implementations is HIPSICLE, and it's demonstrated to work on these processors. So Sickle has had tremendous growth in the last 3 years, with working group participation up 100%. We now have an active presence in supercomputing due to US national lab interest and Intel support for the Aurora supercomputer. We have active open source collaboration implementation using LLVM Clang, which hosts its own weekly meetings. We're seeing adoption now by high performance computing for exascale computing and in the self-driving car domain, using the Renesas R car, as well as in some FPGA, AI, and custom chips domains. We're going to continue to tighten the integration with ISO-C++ and OpenCL, but open to adopting many other forms of backends, which I see there's some questions about that. Look for more open collaborations using GitHub and continue the cadence of ratification every 1.5 to 3 years. And just like ISO-C++, we plan to look ahead to a future where we integrate their features, and we've been actively participating in them along with many other companies on things like executors, coroutines, futures. We plan to adapt the property mechanism in the future, and we're looking closely at adapting things like concepts, modules, and parallel algorithms with ranges. That is something that we pioneered and we've been working on in the background for quite a while. So Sickle 2020, the final version, is coming at the end of this year in a few months. And when it comes out, I want to urge feedback from you to tell us what features you would like to add and that are not currently yet in Sickle 2020 and what you would like to aim for in the future. So the question is, how do you join? I'm glad you asked, or I asked. So in this one slide, you see all the ways you can join Sickle. 3 out of 4 of these need no money. Anyone can suggest a feature or a fix, and a small fee will allow you to participate in the actual design of the features in the working group itself. That's at the bottom in the center circle, and a larger voice in the future of Sickle. So Sickle is creating what we think is a cutting-edge, royalty-free, open standard for heterogeneous C++ compute, vision, and inference acceleration. We have a CppCon tutorial that's coming up on Monday, Tuesday, and Wednesday. And I'm going to show you the time and address. You can still join that Sickle tutorial that's coming up that Gordon and I are going to be teaching. I'm Michael Wong, chair of Sickle, and I encourage you to join Khronos in its effort to lead and accelerate a portfolio of useful standards to enhance your company's leadership. So it is open for all to join, and the key thing I want to highlight is that Sickle is not owned by any one company or dominated by any one company. I will make sure of that. By joining, you can shape Sickle to whatever it is that it wants, whatever it is that you may want to be to serve your particular community better. We have no stake in any one particular hardware, even if you still need to serve a proprietary version of your hardware, and that's understandable. I came from IBM. We had to, make sure that somehow we had to develop further our own hardware when I was at IBM. So I do not believe these are competing. By joining our knowledge, I do think we can serve the world better with the aim of aligning with future C++ standard. I know many people are trying to head in that direction. So as a result, I count many of them as friends in the attempt at trying to get to that stage of furthering C++ standard. But C++ standard does take a little longer, whereas we can change and move a little bit faster. So we want more vendor. They bring valuable platform experience. We want more academics that are involved. They bring terrific research knowledge, and more industry members. And if you'd like to learn more about Sickle, okay, this is the GPU programming class in modern C++ using Sickle that's coming. We've been doing this class for 3 years now. Each year it's gotten more and more advanced. Initially, we did a mix of parallel ISO C++ programming and GPU beginner programming with Sickle. That was 2 years ago. Last year, we got the feedback was great with Sickle. Let's just go to more and more advanced stuff. So we dumped all of the parallel C, all the ISO C++, parallelism, concurrency stuff. Other teachers have done a much better job on some of these. So we focus entirely on the area of our expertise, which is GPU programming. And the feedback from last year to this year is even better, even more advanced stuff. And how does it tie to the latest C++ 17? So even though Sickle 2020 isn't ratified yet, but is well on its way, I've been chairing those meetings every week. There are compilers that have some of these features that are potentially available. So that's what we're going to do in the next in the 3-day course. And with that, I'd like to thank everyone and ask my colleague Gordon Brown to come back on, and so we can answer some of the questions that I'm seeing on the board. So we have about 8 minutes. So starting with the first question, Devon asked, has there been any consideration to introducing smart pointers for USM so we can use RAII for mallocs free? It's a good question. Gordon, do you want to answer that?
Sure. Yeah, thanks. It is a very good question. So far we have the low level API for malloc and free, and then we have the USM allocator as a way of performing USM allocation in standard containers. We have seen some applications create kind of smart pointers that would perform kind of automatic allocation and deallocation using USM. It's not something that's in the provisional specification, but I think it is a good idea, and I think it could be a useful feature for Sickle, either as a tool that can be used on top of Sickle or as something that could be introduced to the standard.
Great.
So I think it's a good idea.
So with that, I think we've answered that question. The next question by Andrew says, how will the upcoming executors feature integrate with Sickle? So I'll just say that we've been deeply involved with this executive, along with many other people like Nvidia, as well as a number of other people from Google and Facebook. So we definitely plan to, so we know it very well, and Gordon has been an instrumental part of being involved in that. So Gordon, can you say something about that?
Yeah, so we've while working on the Sickle specification, the Sickle working group is one of our aims is to try and align with ISO C++ as much as possible for the future. So we've always got one eye on the executor's proposal and what's happening there, both to kind of try to align Sickle with it so that they're compatible and they work well together, and that when executors land in C++, Sickle can kind of move into to use some of those features and work with those concepts, but also to try and kind of shape executors so that supports the Sickle programming model and the Sickle backend as well. So it's been a kind of back and forward between the two standards to make sure that they'll work well together.
So I'll ask this question. So we've been watching participating, and writing the specification for executors. Do you see anything in executors that we have, Gordon, that will make it counter to or impossible to be integrated into Sickle?
No, I wouldn't say so. No, I think the executor's proposal has had a lot of authors on it, and it's been a work in progress for many years now. And I think one of the reasons that it's taken quite a while to get to a final proposal that's now being considered for C++ 23 is that we wanted to make sure that the model was kind of the abstractions were correct for supporting all the various different ways of heterogeneous and asynchronous programming, including things like Sickle and Cuda and various other programming models. So that was really important.
Yeah, a real democratization of all of these different models for different kinds of chips. So next question says, how does Sickle compare to Nvidia's Cuda? So I think that's a great question. And it's not just Nvidia's Cuda. Before Sickle, there were many other frameworks. Some of this is library only, like Nvidia's Thrust. I said Cuda, but it's actually Thrust, the Thrust library. There was actually an AMD Bolt library as well too. There was Boost.compute, which was essentially a C++ framework on top of OpenGL, Khronos OpenGL. And then there's also C++M, which is more properly the pedigree provenance for Sickle. because it introduced the first implicit data movement model. So I would say that I love what Nvidia does with Rust and with Cuda, and I'll also call out that Cuda recently GA'd a new compiler, which is more C++-like, that has better support for C++ libraries, standard libraries, STL. So I would say that all of these are similar in that they were all trying to make sure that they have an STL-like interface. So like Bolt, AMD's Bolt, Nvidia's Thrust, Boost.compute, and C++ and Sickle. So Thrust only essentially, I believe, pretty much supports mostly Nvidia GPUs, but may also work on some CPUs through its OpenMP and TPU backends. Now, there are other people that are much more familiar with Rust here that will answer that much better. So I'm trying to be very careful that I don't say the wrong thing. Bolt, however, AMD's Bolt uses extensions to OpenCL, which are only essentially available on AMD GPUs. And it also provides a Microsoft C++ AMP and Intel TPU backend. The C++ AMP from Microsoft, the only compiler that supports that is mostly Visual C++. I know there are a few open compilers, but it essentially has declined after its flurry of introduction after about 8 years. And that's unfortunate because I actually really liked it. Boost.compute, like I said, was one of the first granddaddies that essentially papered an OpenCL, a C++ wrapper on top of OpenCL. It's a great experiment. And using OpenCL, and it's a great experiment. But we now know that as a way to get to its STL interface. So where Sickle comes in is that Sickle essentially is not just a library; it's also a language and it's a framework. Some part of the library that library calls the call graph handler that you see in Gordon's slide is actually implemented using the Clang front end in the front end itself. So that gives us a much more control over how things are done. The philosophy is that Sickle can be adapted for both as a single all the way front end to back end compiler, or it can be adapted as a separate compilation that is more appropriate to things like in open, like when you're doing graphics or GPU programming or different kinds of device programming, like in autonomous driving, where you might not see you might have a separate compilation system between the CPU code and the GPU code, and they might be separated for 2-3 years before you find out what they are. So in a way, I hope that gives a reasonable overview of not just how Sickle compared to Nvidia's Rust, but how Sickle lives within this whole framework of many, many other frameworks that I've been researching and studying to make sure that all of them gives equal contributions to ISO C++. And in the end, I might also mention the contributions from national labs like Khronos and Raja, which are also essentially library-only frameworks. Okay, but they also build considering building Sickle on top of the backends for Khronos in the high-performance computing space. So that was a long-winded question. We got about 30 seconds left. So next question is great. Would it be possible to integrate coroutine generators with Sickle? I have no questions that is the direction that we will be going. So I want to quickly answer that there's that intention. And then the next question after that says, is there work on getting eigenmatrix operations to use next to Sickle? I'm really glad you answered that. We've been working heavy on trying to get eigenmatrix working in Sickle and contributing some of the changes we need eigen and matrix to work with Sickle. Right now they work with mostly Cuda. So contributing those changes back to eigen, okay, as well as towards TensorFlow. So that is something that we are deeply been involved in. The last one, the next one says, okay, we're really probably running out of time. So I'm going to probably take these, copy so that I can answer them in a blog somewhere. And then
we also have, after this, we have the Ask Me Anything, which I think is in the break after this. I don't know if this will be in the same room, but we can always take a note of the questions and we can follow up there as well.
Yes. I'm going to copy these so that we don't lose them, and then we're going to try to close this session now. Thank you very much for attending. You guys have been wonderful. Keep coming to CppCon. It's a place to learn all about the best way to get heterogeneous computing into C++. And I would say not just for Sickle, but for many other people like Cuda, like Khronos and Rajas and HPX as well too. Thanks. Cheers, everybody. Bye-bye.
Thanks, everyone. Thanks, bye.